faithfully sharing value, exploring great books worldwide. Hi, this is Sally's Book Talk. Today we're diving into the book Reality is Not as You See It for You, and the subtitle is A Journey into Quantum Gravity. The author is Carlo Rovelli, an Italian theoretical physicist who wrote the hit book Seven Brief Lessons on Physics, selling over 1 million copies globally. We at Sally's Book Talk have covered this book before, where it delved into relativity and quantum mechanics in detail. This Reality is Not as You See It is the advanced version of that. Right after publication, it was chosen by Physics World magazine as one of the top 10 books of the year. If Seven Brief Lessons was a sightseeing tour to spark interest, then this Reality is Not as You See It is a deep, mind-blowing dive. Seven Brief Lessons introduced us to the marvels of relativity and quantum mechanics, but it doesn't quite cover the universe's true essence. This book elevates theoretical physics to new heights, guiding you to explore a fresh theory beyond relativity and quantum mechanics, quantum gravity theory. Seriously, it's a theory that shatters your worldview. For instance, he argues that time doesn't exist, space is composed of fragments, and the universe began with a big bounce, not a big bang. All aspects of time's passage are tied to temperature, among other things. These are scientists' imaginative brainstorms. Though not yet proven, it opens up new avenues for exploring the universe. Now, I'll interpret this book for you from two perspectives. First, how quantum gravity theory came to be and evolved. Second, how quantum gravity theory has revolutionized our understanding of the world. First, the author guides us through the development of quantum gravity theory. This journey centers on a core question: what is the world made of? This ancient question, rooted in ancient Greek philosophy, evolved through classical physics, relativity, quantum mechanics, and culminated in quantum gravity theory. Let's go through them one by one. When we think about the world's makeup, we intuitively grasp time, space, and matter. Time and space are easy to understand from daily life. So, what is matter composed of? Over 2,000 years ago in ancient Greece, there was a philosopher named Democritus who proposed a groundbreaking view. He believed that matter has a smallest fundamental unit called the atom, which cannot be divided. This view was unanimously opposed by great philosophers like Plato and Aristotle. Why? Because people couldn't fathom the concept of something indivisible. Matter is a continuous whole. As long as the blade is thin enough, it can be divided infinitely. How could there be something called an atom that can't be split? Democritus made a clever argument. Imagine if you could infinitely divide a piece of matter. What would be left in the end? It definitely wouldn't leave anything with dimension, because as long as dimension exists, it can continue to be divided. So what's left can only be dimensionless points. But now, let's reassemble an infinite number of points together. However, no matter how many points you have, you can't reconstruct anything with dimension, because points themselves have no dimension. Since it's impossible to end up with a bunch of dimensionless points, what remains must be the smallest unit with dimension, a finite number of indivisible particles, that is, atoms. Over 2,000 years later, in 1905, Albert Einstein, just 25 years old, finally found evidence of atoms' existence and measured their size. This debate, which lasted for 23 centuries, finally had an outcome. Matter is indeed made up of indivisible particles. This conclusion is not only the starting point for people's understanding of the world 2,000 years ago, but also the most crucial cornerstone for the quantum gravity theory we'll discuss later. How important is it? Physicist Richard Feynman said that if we lost all scientific knowledge and could only pass one sentence to the next generation, that sentence should be, matter is composed of atoms. Now, the composition of the world has a preliminary answer. Ancient Greek philosophers told us that the world is composed of time, space, and particles. Now we enter the second stage of exploration, classical physics. One of the most brilliant achievements of classical physics is Newton's discovery of gravity. Yet Newton himself once thought his theory was absurd because there was one question he couldn't figure out. Where does gravity actually come from? We say to apply a force to an object, you either push or pull, and you need to touch it, right? That Earth and Sun, billions of miles apart, can still exert force on each other. Newton couldn't find any medium to transmit this force. What's really going on? 2 centuries later, British scientists Faraday and Maxwell found clues to solve the problem. They discovered that there's something called a field in space. For example, hold two magnets close together and you can feel the force between them. It's like invisible lines transmitting force from one magnet to the other. These are called Faraday's lines of force. They're like a huge invisible spider web filling everything around us. This is the discovery of the electromagnetic field. It explains how forces form between adjacent objects. Following this explanation, maybe there's a gravitational field transmitting gravity between forces. This preliminarily solved the problem Newton couldn't figure out. The discovery of fields advanced classical physics understanding of the world. Now, the elements constituting it increased to 5: time, space, particles, electromagnetic field, and gravitational field. Next up, relativity takes the stage. The relativity performed 2 stitching surgeries on these 5 elements, simplifying them to 3. The first surgery is called special relativity, which merged time and space. Our usual concept of time is like this: an event is either in the past or in the future. Time flows like water, moving steadily forward, one moment after another. But special relativity points out that between past and future, there's an intermediate region, neither one nor the other. This intermediate region isn't what we call now. Now is an instant that quickly becomes past. And in special relativity, this intermediate region can be long or short, depending on the event's distance from you. For example, suppose aliens on Mars greet us, and that greeting takes a quarter hour to reach Earth. Now, that quarter hour is the intermediate region. If the person greeting you is right in front, then the intermediate region lasts only nanoseconds, totally imperceptible. But if the person greeting you is on Mars, this time extends to a quarter hour. This quarter hour relative to us is neither in the past nor the future. Why is this? Because light speed is finite. Light takes time to transmit information, making time relative. If aliens were in Andromeda, that quarter hour would become 2 million years. Anything happening during those 2 million years is likewise neither past nor future. So in the cosmos, now doesn't exist. Absolute simultaneity is impossible due to the universe's vastness and light's finite speed. Thus, we discover time and space are intrinsically linked, inseparable. This unified them into a single entity. Space-time. Special relativity unified space-time. Next, the second stitching surgery. General relativity unified space-time with the gravitational field. Earlier we said distant celestial bodies attract via invisible lines in the gravitational field. General relativity states it's simpler. No invisible lines needed because space is the gravitational field. The sun's mass works surrounding space, and Earth merely glides along this curvature. Like driving on a curved highway, you follow the bend. This spatial curvature acts as gravity. Since special relativity fused space and time, not only space but time also bends with gravity. Where gravity is strong, time flows slowly. Where gravity is weak, time flows faster. Place one clock on a mountaintop, another at the base. The mountaintop clock runs faster. Because Earth's gravity is weaker at altitude, even centimeter differences are measurable with modern instruments. Einstein analogized spacetime to a vast, pliable mollusk, ever shaping with us living inside. Now let's recap relativity's logic. Time-space unified, and space-gravity unified. So, time, space, and the gravitational field are actually the same thing. They're all manifestations of the gravitational field. This leaves just three elements composing our world: gravitational field, electromagnetic field, and particles. That significantly simplifies our understanding. But wait, it gets even simpler. Modern physics established its second pillar, quantum mechanics, which streamlined things further. It discovered that among these three elements, the electromagnetic field and particles are actually one entity. In 1900, German physicist Planck proposed while studying electromagnetic waves that energy doesn't change continuously, but in discrete packets. Why this was true, even he didn't understand. 5 years later, Einstein proved these energy packets existed while studying light's properties. Quantum mechanics was born. Einstein said light exists not just as waves, but also as particles. A beam of light transfers energy like delivering individual packets. The carrier of this smallest energy packet is the quantum, the fundamental unit. How does this connect to electromagnetic fields? Electromagnetic fields produce waves that transfer energy in packets, making the field itself a collection of quanta. Thus, electromagnetic fields can be quantized. We see particles and fields aren't separate. Through quantum lens, particles emerge from fields. For example, quantizing electromagnetic fields gives photons. Quantizing electrostatic fields gives electrons. After quantization, electrons appear. Every particle in nature corresponds to a field, meaning particles and fields are one entity, quantum fields. Thus, our world's elements shrank from five to just two: quantum fields and gravitational fields. Can these two merge further? Here comes the book's core, quantum gravity theory, aiming to unify them. Merging, yet exciting, scientific frontier means unifying relativity and quantum mechanics, a tremendously difficult challenge. The two theories are like two separate kingdoms. One rules over large-scale celestial bodies, the other over small-scale particles, and able to understand each other's language, coexisting peacefully without interference. If we try to build a united kingdom with them, what would happen? Suppose we want to observe a very tiny region in spacetime. We need to place a particle there as a marker. According to the quantum uncertainty principle, a particle can't have a definite position in space. It escapes quickly. The smaller the region, the faster it escapes. The higher its speed, the greater its energy. Based on general relativity, an object with huge energy causes space to curve. In an extremely small region, space collapses into a black hole. Then the particle would fall into the black hole, and we'd never find it again. That is, we can't measure an extremely small region in space. Because this region would fall into a black hole, this creates an incompatibility between quantum mechanics and general relativity, so forcing them to unify would lead to collapse. We need to negotiate. The key issue is how small this tiny region can be. Is it infinitely small? If we use the traditional view, treating space as an infinitely divisible continuum, allowing a piece of space to be infinitely small, in the incompatibility problem arises that if we shift perspective, suppose space has a smallest unit of division, then could the two coexist harmoniously? John Wheeler, the American physicist who coined black hole, proposed a view of space. In the macro world, space is smooth and continuous, but in the micro world, it's fragmented with a smallest volume unit. Wheeler invented an equation describing this. Its solutions depend on closed loops, a loop being a circle, so the theory is named loop quantum gravity. Remember the Faraday lines of force in electromagnetic fields? In Wheeler's equation solutions, these loops are like Faraday lines in the gravitational field. They form the field and weave space. Or kind of space is woven. Our past understanding of continuous space is like tilting a cup full of water. Water flows out slowly and continuously. In loop quantum gravity, space, replace water with mung beans and tilt again. Beans roll out one by one. These mung beans represent the smallest unit of volume in space. It's discontinuous and not infinitely divisible. Through this concept of fragmented space, we've quantized space. Space is assembled from these particle building blocks. Space is fragmented. What about time? Special relativity says time is local, with each object having its own time. But loop quantum gravity goes further, abandoning even local time concepts. In loop quantum gravity equations, time simply doesn't appear. The variable of time vanishes. What does it mean when we say time disappears? First, we need to understand what time actually is. Our time measuring tools are clocks, but before clocks existed, how did people perceive time in the past? Galileo discovered that pulse beats could measure a chandelier's swing time. Based on swing isochronism, people invented pendulums. Later, doctors used pendulums to measure patients' pulses. Notice how this became a cycle. Galileo used pulses to measure pendulums, while doctors used pendulums to measure pulses. Actually, time is just an intermediary. We've never measured time itself. We only measure physical quantities like pulse and pendulum, then observe their correlated changes. So-called time is merely a hypothetical aid for observation, like drawing auxiliary lines in geometry problems. These lines don't actually exist but help solve problems. Just like these auxiliary lines. Now, space is dismembered, time has vanished, and the world undergoes reassembly. Time is quantized, with gravitational and quantum fields reconciling. Returning to our original question, what is the world made of? The answer is now simple. The world has only one element, whether particles, light, energy, or space-time. All are manifestations of a single field. We call it the covariant quantum field. Over centuries, as science grew more complex, the world became simpler. This is the picture loop quantum gravity paints. Next, let's explore how loop quantum gravity's world brings disruptive insights that transform our familiar reality. First insight, rethinking time. Just now we said loop quantum gravity is a theory without time. It tells us time doesn't exist, and so-called time is just an auxiliary tool. That there's something missing here, isn't there? Because using correlated changes of two physical quantities only measures time's duration, but time has a more crucial feature. It has direction. If the microscopic world doesn't need the concept of time, how do we explain the microscopic world? Well, what about the phenomenon we genuinely feel, that time never returns? The answer is simple. Time and heat are similar. Let's first chat about heat. Recall scenarios without heat transfer, like a pendulum swinging back and forth, or a stone thrown up and falling down. These processes are reversible. Now, shift focus to scenarios with heat transfer, like a burning candle emitting smoke, or a cup of hot tea cooling down slowly. These processes are irreversible. You can't turn smoke back into a candle or make the heat lost in the air reheat the tea. From the moment heat transfers, the process is irreversible. Isn't this characteristic very similar to time? It can only move forward, not backward. If you think carefully, you'll find that all phenomena involving time's passage are related to heat, and only heat distinguishes. Examples like this are everywhere between past and future. Life ages because the body generates heat. The bicycle wears out due to friction producing heat. Even the moon orbiting Earth generates heat. The moon causes tides which slightly heat the ocean, thereby exchanging energy with the moon. If the seemingly eternal moon is actually slowly moving away from us, and whenever you think of a phenomenon that demonstrates time's passage, you'll find it's proven through heat generation. Heat is the only physical variable related to irreversible phenomena, and it plays the role of time. Therefore, to better understand time's essence, We must reverse our previous understanding. It's not that time's passage causes heat consumption, but rather heat consumption causes time's passage. Having discussed time, now let's talk about space, as brought to us by loop quantum gravity. Second insight, everything in the world is interconnected. All things are linked. This term is often considered a hallmark of the internet era. But did you know? The world's fundamental nature is universal interconnectedness. Quantum mechanics reveals particles only become describable when interacting or colliding. When isolated and inactive, it's like a ghost, existing nowhere. Essentially, the quantum world thrives on social interaction. Isolated quanta are meaningless. Only connections matter. Through these interactions, the world transmits and shares information. For instance, your cells carry ancestral data, while light entering our eyes conveys information about objects it encountered. Thus, the world is a relational network, a web of information exchange among physical systems. Quantum gravity offers an even more imaginative take on this network. Earlier, we mentioned space comprises the discrete particles that link and bond. Typically, they interact only with neighbors, forming stable space. But add a connection between distant particles, like giving them phones for instant communication, and spatial shortcuts emerge. Quantum gravity explains entanglement through these shortcuts. Distant particles sense each other via connections. We can speculate further. An intensely hot early universe had energy to connect nearly all particles. Everything was interlinked. As the universe cooled, connections broke like a crumpled paper unfolding into current space-time. Our modern communication concepts echo the universe's past. Connection is nature's instinct, and social networks mimic the pre-cooling cosmic state. Universal connectivity might be written in the cosmos DNA, transcending time and space. From a grander view, loop quantum gravity reveals a third insight. The universe began not with a big bang, but a big bounce. This deduction is astonishing, since the Big Bang Theory is universally known. It describes the universe exploding from a dense, hot singularity, a concept from general relativity. Its equations predict that the universe originated from an infinitely small point, the starting point of time and space. Hold on, do you see the problem here? We've repeatedly emphasized that in the physical world, there's no concept of infinitely small. Both matter and space have a lower limit to their scale. General relativity deduces the concept of a singularity because it assumes space is infinitely divisible. Not just relativity, many physics calculations yield meaningless infinite results from this same assumption. But when we incorporate quantum gravity, these infinities vanish, and the anomalous concept of a singularity disappears. If this singularity vanishes, where did the universe come from then? Imagine a dense universe, squeezed incredibly small by its immense weight. When it hits space's smallest scale and keeps compressing, pressure turns to resistance, like a spring compressed to its limit, causing a big bounce expansion that formed today's universe. But this explanation perfectly avoids the singularity. This bizarre concept makes the universe's origin meaningful and researchable. That covers the main content of this book. Looking back on this quantum gravity journey, we've continuously simplified the fundamental elements of the world. Ultimately, with quantum gravity, we achieved a grand unification of the world, overturning our traditional understanding of the universe. 2,000 years ago, ancient Greek philosophers' deepest insight was proposing that particles are infinitely divisible. 2,000 years later, quantum gravity's fundamental view is that space isn't infinitely divisible. The world has no infinity. The same insight. Separated by 2 millennia, human exploration seems cyclical. The cosmos is vast but has scale. The universe is complex but has limits. This is physics key. If there's anything truly infinite in the world, the only answer is our curiosity about the universe. All right, reality is not as you see it. That concludes our interpretation of this book. Listening notes are below the audio. See you tomorrow.